So this is your Vy, right? So for this case, you have to consider the entire area. Okay. Right? You have to consider, because this is where element B is. Okay, this is where your element B is. Yeah, this is where your element B is. So from here, so if I'm not wrong, this is 0.205. Yeah, I think that's 0.166. Let me be very sure. That is 0.166. I'm correct. This value over here, which is my TF. TF is equal to 11.8. Okay, so TF is 11.8 millimeters. I'll remember that. And then TW is 7.24. Okay, 7.24. Now, even the solution manual got this wrong. Okay, sometimes I check the solution manual. What they see as DW and TF is wrong. Okay. Okay. So let's apply that. So we know that Vy is equal to 25 times 10 to the power 3. That we know. Ixx, we know that is a number. I don't know why is it. It's 40.8. Okay, 40.8 times 10 to the power minus 6 meter 4. And then T, thickness, is equal to TW because we're interested in element B, yes or no? And this is 7.24 times 10 to the power minus 3 meters. Okay. And then we can go from there. Okay. So we want to find Q. So you have to write out the formula first. Okay. So the shear in XZ is equal to Vy over Ixx Qx divided by T. So Qx is equal to V y bar. Okay. So this is the y distance. Okay. So I can remember where is y, because now what is this distance? Okay. You can go crazy. Okay. So Qx is equal to Q of flange plus by Q of web. Okay. So the width is 0.166. The depth is 11.8. Right. And then the y bar is 0.205 minus by 11.8 times 10 to the power minus 3 divided by 2. Okay. Then plus. Okay. Plus by what? Plus by the width is now 7.24. No, let me bring this closer. Okay. So I'm going to compute this first. Okay. So this will be equal. I'm going to compute the flange first. Okay. 0.205 divided by 2 minus by 11.8 power minus 3 divided by 2 times by 11.8 power minus 3 times by 0.166 is equal to 189.22, okay, times 10 to the power minus 6 meter cube. Let me try again. 0.205 divided by 2 minus 11.8 power minus 3 divided by 2 times by 11.8 power minus 3 times by 0.166. 189.22, correct. So now I'm going to consider the web plus. So now the web is 7.25, the width is 7.25 or 0.24 times 10 to the power minus 3. Now the depth I have to be careful. Okay, so 0.205 divided by 2 minus by 11.8 times 10 to the power minus 3. Okay, so why? Because this is the distance I want now. right? So that's why 0.205 divided by 2 minus by 11.8. Okay. Then I will take the same value, 0.205 minus 2 minus by 11.8 times 10 to the power minus 3. And then I will divide the whole thing by 2. Okay, because it's centroid. So plus, okay, 0.205 divided by 2 minus 11.8 power minus 3, because the same, I squared both times. Divide by 2 times by 7.24 power minus 3. So this will be 29.780 times 10 to the power minus 6. I'll do it again. 0.205 divided by 2 minus 11.8 power minus 3. Squared divided by 2 times by 7.24 power minus 3. 29.780. So this will be equal to 189.22 power minus 6 plus 29.780 power minus 6 is equal to 219 times 10 to the power minus 6 meter cube. Let me do it. 189.22 plus by 29.78. 219. Okay. So now we got everything. The shear XZ is equal to Vy 219 divided by 40.8 divide by 7.24. Okay, so 25 power 3, 219 power minus 6, Eugene. Come on, come on. Divide by 40.8 power minus 6 divided by 7.24 power minus 3 is equal to 18. Now I'm going to 535. I think I'm going to calculate the principal stress for you to highlight what I mean by earlier. Okay, so 25 power 3 divided by 219 power 25 power 3 divided by 219 power minus 6 divided by 40.8 power minus 6 divided by 7.24 power minus 3. Hey, 25 power 3 times 219 power minus 6 divided by 40.8 power minus 6 divided by 7.24 power minus 3. 18. Okay. So 18 point, so it's going this way, right? Okay. So now we put everything in. We look at the element now. Okay, I'm going to get our element. Okay, now this is our element. Right. So our element states that the shear is going in the other direction, and it's equal to 18.535 times 10 to the power 6 Pascal. Now, this is where it gets critical. Now the shear is pretty high now. Can you see that? Okay, now the shear is pretty high. So if we are going to calculate, I'm not going to draw, okay, I'm just going to sketch Mohs circle for you, okay? Just, okay, I'm going to draw. I hate doing things that are like half neither here nor there. It bothers me big time. Okay. So now we're going to sketch. Okay, so I'm not going to do a big sketch. So this is 0, 5, 10, 15, 20, 25 normal stress, minus 5, minus 10. Okay. And then we have our shear. So 5, 10, not enough space. Do I have space? I have space. Sorry. Okay. I know I went too much. Okay. So 5, 10, 15, 20. So this is our shear. Minus 5, minus 10, minus 15, minus 20. Okay. So we know that our one of stress is at 14, okay, tensile. 14.9. So I'm going to call it 15, dead on 15. So this is our stress Z. Okay. We know that our stress X, point X is definitely over here. Okay. And this is our stress Y line. And the shear is 18.53. Okay. So 15, 17.5, 18.53. So 20. Okay. I'll take it at the center. Okay, give and take. Okay. So is now point Z is going in a clockwise direction. Okay, clockwise and anti-clockwise. So this is our point Z. This is our point Y. Okay, so we draw the center now. Right. Now we cannot just rely. Remember the previous stress state, we can just say, okay, why not we use the normal stress in the Z direction, choose a material, fine. This one you cannot anymore. Why? Okay, because we're going to calculate our principal stress. So the stress average, give me another like 5 minutes, okay? So the stress average is equal to 18.535. No, not 18.535, come on. It's equal to what is 14.958 plus by 0 divided by 2. Right? So it's 14.958 divided by 2 is 7.479. 7.479 times 10 to the power 6 Pascal. Okay, so we found our center. Okay, our point O. Then we find our tau max, which is the radius of the circle. So it's 7.479 squared plus 7.479 squared plus by the 18.535. Okay. So 7.479 squared plus by 18.535 squared, square root of the whole thing is equal to 20. So your stress A and stress B is equal to 7.479 plus or minus 20. Okay, so it's 27.479 and 7.479 minus by 20, minus by 12.521 megapascal. All these are all megapascal. Okay, so now you realize that if we were to not analyze the shear, we are in trouble. You cannot just use the normal stress. Okay, a lot of engineers, okay, no name mentioned, because it's too difficult to calculate. Let's assume that the normal stress is the highest. You cannot make an assumption like that. You make an assumption like that, you know, if I found that out that any of you make this assumption as a true engineer, guess what? I'll come after you, man. I will, man. Okay. I'm sorry, but I will. Okay. So now we know that the maximum is at 20. Right. And then this is 27.5. So this is 27 point, yeah, about 12.5 is about here. Come on. Okay, so I need to make it to 20. Okay, and then you have to check. what do I mean that you have to, we have to check, right? So now we know that that is one circle, so that belongs to our what? That belongs to our YZ plane. Okay, so the next one is our XY plane. So I'm going to draw our XY plane circle. Okay, so as engineers, when we were asked to do calculation, we have to show all this. Why? Because if a building were to collapse or a structure were to fail based on your analysis, and when I am the expert witness, I will know what is missing. You all see what I mean? What is missing in your analysis, and I will know, or any, I won't say any expert witness will know, but if we are called upon being an expert witness on any situation, okay, 2, 4, 6, 8, 10, 11, 5.5, we will know. Okay, so if I were to see a comprehensive drawing like this, okay, the person know what he or she is doing. Okay, 2, 4, 5, 5.5. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5.5. 1, 2, 3, 4, 5, 5. Okay, and this belongs to your XZ plane. Okay, and if we were to if this drawing has been shown or this calculation has been shown as a professional engineer or chartered engineer, then we will sign our name, okay, and the structure is soundly designed and calculated. Okay, not like, I mean, this we happen to be lucky. This happened to be lucky, right? The angle, the principal plane angle is so small. Oh, the value is about the same. You can use normal stress. But when we look at the next element, no more. Okay, that's where we have to construct 3D mold circle. Okay, if that's the case, now this week the homework will be the same as last week. Now we can do last week homework properly. Okay, next week got one more topic, which is bending moment and shear force. Okay, I don't think it depends on time whether I can include deflection or not, but I'm not too worried about that. Okay, on that note, yeah, I'll see you guys next week. So the tablet I'm using is what tablet am I using? Let me stop recording before I answer that question.